FEMA P-1100 has a stipulation where you're supposed to put a shear wall on each end of a cripple wall. Now this sounds very easy, it sounds like a good idea. New construction is designed that way, and but it has some problems from a contractor's point of view, and let me show you what those are. From a contractor's point of view, when he has to move all his equipment in two different places, it costs a lot of money. So let's say he's here and he's got all his bolts and he's bolting everything and he's got all his, his drills and all this equipment he has, drags the plywood in, all that stuff. And let's say the access is over here. So he comes in here, and what he'll normally do is he'll find the one that's the closest to the access where there aren't a bunch of pipes and stuff in the way. And then he'll make his panel as long as he can, as long as required, rather than dragging everything over here and having to do the whole thing all over again. Now, it is a very easy procedure to make it so it does not matter where you put it. So a contractor can go under the house, he can figure out, okay, I need to put in 12 feet here, should I put it on this end, put it that end, am I going to remove plumbing, do I have to remove ducts, find the easiest place to do it, which in turn is the cheapest for him, and in turn is the cheapest for the owner. And this requires just simple procedure, and I'm going to show you what that is right now. First, let me show you what the problem is if you put the shear wall in only one location. So here is our shear wall right here, and what it's done is it's connected this whole part of the cripple wall to the foundation. And the reason I say only one part is if you look right here, you'll see that there's a break in the upper top plate. And all the toenails from all these joists right here, and if you put framing anchors, say some L90s or something else, and attach them all to this top plate, what can happen is this entire floor, as it transfers the load into the upper top plate, it will pull this way, and when it does so, it'll pull onto where this break is, and that load cannot make it back to the shear wall. And because it can't make it back to the shear wall, we have really not protected this entire section of the house. So what P-1100 has done, it has taken a steel strap and it's attached, it's straddled this break right here, so that this part of the cripple wall and this part of the cripple wall are attached to each other. And we're going to go ahead and see how they did that. So this right here is the break, also known as a joint in P-1100. And the problem is that this upper top plate and this upper top plate are no longer connected because of this break. And what that means is this part of the cripple wall and this part of the cripple wall are independent of each other, such that if I put a shear wall over here on this side, it would not be connected to this side, because when you put in a shear wall, you always nail it to the upper top plate. If there's a break in the upper top plate, naturally this shear wall is going to be disconnected to that. Now what they've done, the strap they've used, you can see it right here, that is the strap. And we're going to assume they use a Simpson Strong Tie MST A36 with a value of 2,050 pounds. And the reason I say we can assume that is because, as we saw in the rest of the connector tables, they always use the product which had the lowest value as a safety factor. So we will assume that. So if we look at the catalog, or we look the way it's installed here, we can see that it says it's going to take 14 8D nails each side of the joint, so that means we're going to put 14 nails on this side and 14 nails on that side. Now the interesting thing is that the MST A36 strap actually takes a total of 26. It's all it can take. It can't take a total of 28. So over here it says it's taking a total of 28. In fact, it can only take a 26. And on top of that, rather than an 8 penny nail, which is 131 thousandths, you're required to use a 10 penny nail, or 0.148 thousandths, and these are 2.5 inches long. So here we have the longest, we have the wrong size nail again, and wrong thickness, and so what the actual capacity is, I don't know. Someone would need to do those calculations or call Simpson up. But anyway, the idea of the steel strap, I hope you understand. I'd like to point out, if we use a steel strap here and perhaps there's another break over here, we won't be able to put in our shear walls because we can't nail into, through the strap. Nor do we want to put the strap over the plywood because then it will put too many nails into the upper top plate and it might split. Right now, I'd like to look at another way of addressing the breaks in the upper top plates. And if you look on the upper left, the number there of 188 pounds, that comes from the American Wood Council connector calculator. So that's how much capacity, lateral capacity, single shear, a nail, a 12-penny nail has. And that's what we use when we make this connection. So let me show you what we've done here. On this side of the break over here, normally we'll put in 30 nails, and over here we'll put in 30 nails. Now the reason we put in 30 is in a nail gun they have two clips. Each one is 30 nails. So we have 30 nails, shoot those nails, then we take the other clip and we shoot them on the other side. So in the end we have 30 nails on each side of our break. And it takes, I don't know, at the most, 1.5 minutes, 2 minutes for each side. You can go as fast as your compressor will allow you to go. I mean, if your compressor is strong enough, you can literally do it in 30 seconds. So this is a very, very fast way of doing it. If you had to get the strap, you got to drag the strap under there. You got to get a special 2.5-inch long nail that's made for these. You got to bring your palm nailer out, and then when you're all done, you don't have near the capacity of your connection is not nearly as strong. Plus, you can't put your shear walls there, so it has all sorts of downsides, the steel straps do, and this has, I would say, nothing but upsides. And so when we're all done with it, we end up with 30 nails, and we multiply that 188 pounds, which we just looked at, and our connection now resists 5,640 pounds. Now, a 2x4 has a tensile strength of about a little over 7,000 pounds. If it's a full 2x, it's more than that. So we could put in as many nails as we wanted and probably get up to 7,000 pounds. So let's see what those nails do to make sure that the entire house is connected to our shear wall. So this right here is the floor that you walk around on. And then this is a floor joist that supports the floor. And you see how this floor joist, there's a nail that comes in here and a nail that comes in here. There's a nail that comes in here, and then there's a nail that comes in here. So when the floor tries to move, it goes into that floor joist and into the nails, see the nails right here, which in turn go to the upper top plate. So the upper top plate is going to move that way as the floor goes this way. When it goes that way, it pulls on these nails right here in the upper top plate. When those nails pull this way, they in turn pull down the lower top plate, because you see how the nails come up from the lower top plate into the upper top plate, lower top plate up there. So they're connected. So the nails pull this way, and when they pull this way, they pull on the lower top plate, and then they pull into these nails again on the lower top plate, which are connected to the nails, connected to the upper top plate right here. So now it pulls on the upper top plate, which then in turn pull against the nails on top of our shear wall, and then all the force goes into our shear wall, which is right where it belongs. So let's go ahead and look at the big picture on that. So here we have the break in the top plate. This entire, cripple wall and floor and everything is disconnected from our shear wall. So now what we've done is we put a whole bunch of nails on this side of the break, a whole bunch of nails on this side of the break. So when the earthquake force comes this way, it travels, through the nails into the lower top plate, because remember, the nails go into the upper and into the lower. So it goes into the nails in the upper top plate. Those in turn are connected to the lower top plate, so then the lower top plate goes this way, comes over to the nails right here. Those nails are connected to the upper top plate right here. So what finally happens is all the force gets pulled on that upper top plate, and this is where all the nails are in the upper top plate. And so all the force is transferred into the shear wall where it belongs. Once we join the top plates together, basically the upper top plate all along here is a solid piece of wood because they've been joined together so strongly. So what that means is wherever you put the shear wall, it will absorb the load no matter where the load comes from. So we can put the shear wall right here in the middle. we can put it right here on the end, or we can put it here on this end, or we can put it on this end and that end if, you know, if we need to. Again, in seismic retrofit work, the big problem that we always have is access. Not only is it difficult to work in because there's very little clearance, but also there's just all kinds of junk on there that you would not see otherwise. And underneath a house, they don't care what it looks like. They'll throw crap everywhere. They'll put everything on the wall. They put heating ducts along the wall. They put pipes, plumbing. They just put all kinds of junk up there. And from a contractor's point of view, the main thing is you just need to be able to work at one location, and so you don't have to drag your tools around. And at the same location, you put in the bolts, because all earthquake load goes into the bolts that are attached to the plywood. And then you do the same for your framing anchors up above. So you can do everything in one spot. Saves a whole lot of time, saves a whole lot of money, and saves the homeowner a lot of money, and makes it so the retrofit is more affordable. It is probably clear why these top plate splices are so important. Behind me you see a detail from a retrofit guideline called Standard Plan A. And in that guideline, naturally, as you can see, it requires these top plate splices using a steel strap. Now, we've done about, I don't know, 150 to 200 Standard Plan A retrofits through the Earthquake Bolt and Brace program, partially through the City of Berkeley, and partially because customers have asked for it. When we've done these, we've always used the nailing system that I just showed you, and not once has a building inspector who's actually crawled into the house, which is in itself very rare. Not once has anyone bothered to look at the upper top plate breaks to see if there was a steel strap. And this is even including the city of San Leandro, where they actually teach a class in how to use Standard Plan A. And in fact, I went there to help them, or to observe, and to help the people figure out how to use it. And in that class, these straps were never mentioned once. So these straps are extremely important, and they need to be made simple. It needs to be made quick. It needs to be explained to contractor why you need them. And overall, the standard should be something that people respect as a place to go to find out how to do something right, how to do it well, and still be able to make a living doing it. So this sort of connection using the nails, because it's fast, it's very efficient, it's very effective. It is something that if contractors know about it, they'll want to do it, and they will respect the standard because they'll see the standard as something that is helping them. Otherwise, they will tell the homeowner this thing is a piece of junk. It just makes it a lot more expensive. For example, these upper top plates is telling us how to do it, but it's really slow and not as strong, and people will simply say they don't want to use it.